Today we have the distinct pleasure of having Stefan Ledinger here with us from Biocrates. Biocrates, it really is a company that puts a stake in the ground regarding the complexity of the hunt of biomarkers for the type 1 diabetes prodrome space, and how omics can elucidate it to advance precision medicine. The title for the talk is Type 1 Diabetes as a Complex Metabolic Disease, Metabolomics as a Tool to Explore Pathophysiology and Enable Personalized Medicine. And just a short bio for Stefan Ledinger. He's been working in life science industry for more than 15 years. After graduating in bioengineering and business economics, he started his career in various functions in the field of routine diagnostics. In his current position as director and business development with Biocrates Life Sciences, he works with scientists in academia and industry to conduct metabolomics projects in various areas of biomedical research, including basic and clinical sciences, epidemiology, as well as all stages of pharmaceutical R&D. Across indications, the association between autoimmunity and metabolism is a matter of growing interest. Thank you very much for joining us, Stefan. I really appreciate it. And Biocrates is very, very interesting. We've been following it on social media. And the tweets and the the content you provide is quite timely and also, as I said before, interesting. So welcome.
Thank you, Monica. It's a pleasure to be here and to be invited. As my short bio already said, we get to see a lot of diseases, a lot of indications, certainly not just type 1 diabetes. And to us, it's really interesting to try help our customers and partners figure out those diseases, but also to see how many diseases share certain features, right? And it doesn't matter whether we're talking about diabetes or neurodegenerative diseases or cancers. Those are all complex diseases that might share more features than we would think. So on the next couple slides, I will talk about type 1 diabetes, but I will not purely and only talk about diabetes, because sometimes I think there's learnings and inferences that you can make from other fields of biomedical research as well.
Sounds good.
So first of all, I will get started by discussing a little bit about the medical need that there still is. Type 1 diabetes researchers certainly know it a great deal better than I do, but I'll still show a couple things. I will go into a couple specific metabolic pathways that might be interesting in the context of type 1 diabetes. I will show some case studies, and if there's any time left, we can briefly talk about how one might go about starting their metabolomic study. So the medical need for metabolomics in type 1 diabetes research, and it starts with pathophysiology. To us, it always starts with pathophysiology. It doesn't, but you don't do metabolomics for the sake of doing metabolomics. You do metabolomics for the sake of understanding pathophysiology. What is the potential for therapy stratification using metabolomics? And I'll show a specific example from another indication, actually, how metabolism is important in shaping therapeutic responses. I obviously have to go very quick with the limited time we have. Each of those topics would warrant 30 minutes of presentation in and of themselves, and I will cut it down to one slide each.
No worries. So, if people want more, they can reach out to you directly.
Absolutely. Absolutely. So obviously, type 1 diabetes is an autoimmune disease, but still the pathogenesis of the disease is not completely understood, involving genetics, involving microbiota, but also involving environmental factors, nutrition, and lifestyle. And metabolomics is certainly a good way to study those things. We'll touch upon some of those factors specifically later in the talk. The second area of interest, of course, is to understand how metabolism drives later stage events in people with type 1 diabetes, because they pretty much have similar late stage comorbidities and outcomes as someone, for example, with type 2 diabetes might have. And in times like these, with the Western style diet, many people with type 1 diabetes don't just have type 1 diabetes, they also have the typical risk factors that are associated with Western lifestyle. So metabolomics could help understand these. We do think that one of the key areas where metabolomics could really help going into the clinics is therapy stratification. And thankfully, after many, many years of research, now there are more options than just insulin for patients with type 1 diabetes, and more are certainly coming up in the future. But as we are coming to a situation where there are treatment options to prevent or to treat type 1 diabetes, we will also get into a discussion for which patient is a certain drug actually suitable. And it doesn't matter, you can take any medication in any disease, and you will have some non-responders in there. It's not so many maybe for metformin, but for a typical multiple sclerosis drug, it is a large thing. We do think that metabolomics could help stratify patients based on their biochemical phenotype rather than only their clinical phenotype, because it is very rich in information. It is also richer in information than what you would typically get from routine biochemistry. The second area certainly is disease monitoring and finding out when a patient is progressing. It is estimated that about 5 to 10% of diabetes patients need to change therapy. That's mainly, of course, type 2 diabetes. But unlike in cancer, where it's often acquired resistance that forces a change in therapy, in diabetes, it's probably more due to progression than anything else. And of course, also metabolomics could be used to find out whether there's an increased risk of a disease-related event, for example, a cardiovascular event. The interesting thing here is, of course, that metabolomics can cover the disease across the patient journey and is flexible and can change as the disease progresses. That's certainly a big advantage over genetics. The third area is lack of actionable biomarkers. I have been to a biomarker conference just last week, and as of 2023, it's still the case that almost all indications where there are companion diagnostic biomarkers are in oncology. There's almost nothing in other indications, and part of it is because you can't test for a driver mutation or anything like that in diabetes.
What can I ask? Which conference was that, Stefan?
It was the Clinical Biomarkers and CDX conference in London.
Okay. Yeah, there are biomarkers for type 1 diabetes, but they're not widely available to the clinic general practice.
And in this case, of course, it was not diagnostic biomarkers, it was companion diagnostic biomarkers, and that's right. Still more tricky, right? True. And where there's also close to nothing is a truly integrated approach, right? Even with those CDX that are around for oncology, it is, should the patient get this drug or should the patient not get this drug? But in terms of co-medication, stratified approaches for nutrition and lifestyle therapy, there's nothing available. That's pretty much still based on trial and error. And we think that metabolomics could help doing better there. Really define therapeutic choices beyond the main drug that you might want to give the patient based on the biochemical mode of action of those interventions. We'll come to a very specific example on the next slide.
Okay.
At Biocrates, we would call the approach that I'm about to show you performance companion diagnostics, in the sense that it goes further than a typical companion diagnostic would do. There's nothing that I could show for type 1 diabetes, but we have some proof of concept studies, and what is shown on this slide is from immune checkpoint inhibition, where it has been shown that a certain type of lipids, together with age, was very, very good in predicting who was going to respond and who was not going to respond. That's obviously something that you would also aim for doing with a typical CDX, like PD-1 expression. But the study here went a little bit further than just saying, okay, we have a signature for a responder and a signature for a non-responder. The study actually showed that there might be ways of using the metabolomics result in actually defining the co-medication that you could give the patient in order to boost the response, to essentially make a non-responder into a responder. Because the lipids that they found to be reduced in those that were non-responders are essentially lipids that you would find in fatty fish or in fish oil. So the speculation there was that you could maybe give the patient fish oil or recommend them to eat fish on a more regular basis, and in this way increase those lipids that are apparently essential for response to chemotherapy. We have other examples as well, like recently for pancreatic cancer, where a microbial metabolite has been found to be essential for response, and there it has actually been shown experimentally that supplementing this specific metabolite actually works in improving the response to therapy. So that was what I wanted to show in terms of the medical needs that we still have to address in type 1 diabetes. And as promised, there's two specific areas of metabolism that I wanted to address because they clearly are associated with the pathophysiology that we're seeing. So it's well known by now that the microbiome does have something to do with type 1 diabetes pathogenesis, and the way that most microbiome research is done today is that you measure that you measure the microbial genome in a fecal sample, and that's all nice and good, but composition in itself does not necessarily tell you a lot about the function, and also you have feces only available, and most of the interaction between the host and the microbiome actually occurs higher upstream in the gastrointestinal tract. So we have a fair number of researchers who came to the conclusion that having the genomic information of the microbiome is not enough, and you actually need to add something that gives functional insights, and maybe something that provides functional insights on a systemic level. And metabolites are ideal in this way because for some metabolites it's very well known that they are produced and maybe exclusively produced by the microbiome, and you can measure them as part of a metabolomic study in a serum or plasma sample.
Yeah, it's an important point.
And without going in too much detail here, for several metabolites, several microbial metabolites, it is very well established that they are playing a role in different diseases that might in part be relevant here, like secondary bile acids and liver function. TMAO and cardiovascular diseases is was maybe the first major indication where this has been reported. And indoles and short-chain fatty acids is very much associated with immune function. Now, some of you might say, all right, if I'm interested in bile acids, I can get a measurement of bile acids from my central lab. Isn't this good enough? And yes, it is. It is the current standard to use the sum of bile acids. But actually, not all bile acids are created equal. There's primary bile acids that are produced in the liver as the endpoint of cholesterol metabolism. And then there's secondary bile acids that are produced by the microbiome. And those secondary and primary bile acids have different signaling pathways. They have different affinity for the respective pathways, of course. And in case of the secondary bile acids, most of them are cytotoxic and are involved in the inflammation, or are involved in inflammation, might be involved in inflammation that you might see going on in type 1 diabetes. Not too long back, I mean, you could look at a review from 2009, 2010, or something like that. That's really where the field of bile acids research has really started off, because they have always been known to be important, but it has been assumed that they are important for the digestion of dietary lipids. And only now, or only in the last decade or so, have bile acids really been acknowledged for their important biological functions in a vast variety of tissues and cells. Obviously, of importance here is that FXR, the main receptor for the primary bile acids, is expressed in pancreatic beta cells. And I still keep being surprised that FXR is expressed in platelets and appears to affect platelet function, although platelets don't even have a nucleus, and FXR is a nuclear receptor. So there's obviously a non-genomic way how FXR also affects the function of their target tissues. So coming to a conclusion for the bile acids part, especially the primary bile acids signal through the FXR receptor, and as a nuclear receptor, this regulates a vast variety of biological functions and metabolic pathways, including glucose metabolism, which is obviously of importance here, but also triglyceride and cholesterol metabolism. And bile acids also regulate their own production. And as mentioned, they do have immune regulatory function as well. The second pathway that I wanted to show is the tryptophan pathway. And it's actually 3 pathways, all originating from tryptophan. One is the serotonin pathway, so neurotransmitter producing pathway, if you will. And it is involved in gut-brain signaling and gut motility, for example. So there is some relevance maybe to the microbial component of type 1 diabetes. The kynurenine pathway is hugely interesting for many immunologists because it is so intimately involved in immune regulation. And then there's indoles, which are actually microbial products of tryptophan. So they also have a role in gut homeostasis, but also in immune regulation, and also in regulating expression programs via yet another receptor. This is just an overview over the 3 branches of tryptophan metabolism. And while I haven't looked into each specific metabolite along the pathway, it has been shown, for example, that here this intranilic acid is typically increased in type 1 diabetes, while it is not increased in type 2 diabetes. It doesn't appear to be clear what the exact function is, but there might be a role of this specific molecule and the corresponding enzyme in the immune component of type 1 diabetes. This leads me to the end of showing specific pathways. There's dozens and dozens of different metabolic pathways, so this was by no means intended to be a complete overview of metabolism in type 1 diabetes. Also, not everything is understood. The point is, we understand quite a bit about the pathophysiology of type 1 diabetes. We also understand quite a bit about metabolic pathways and how they are built and what are the intermediates, but we don't necessarily know the exact function of each specific metabolic pathway in the disease. Okay, we're already advancing quite a bit in time, so let's go through a couple case studies. And I have chosen one here from 2013. That's an oldie, but it's a goldie. It's type 1 diabetes, and it's the first example to our knowledge, or the first that we have become aware at Biocrates, where metabolomics has actually been used in an autoimmune study and in a microbiome study. So basically, what the researchers there did was take a type 1 diabetes model and gave the male microbiota to female mice, which normalized the gender ratio for the incidence of type 1 diabetes. But then when they blocked testosterone production, the gender ratio in the type 1 diabetes incidence went back to normal. So there apparently is a way how the microbiome affects steroid hormone metabolism, and in this way also type 1 diabetes incidence. Metabolically, it might be more complex than just microbiome affecting testosterone production directly, because there were a couple of other metabolic pathways involved in the study that also almost completely would have explained the gender difference in type 1 diabetes incidence. The second example from type 1 diabetes that I have brought you here is a much more recent paper from 2022 that showed that dysregulation of secondary bile acids precedes islet autoimmunity in type 1 diabetes. Without going too much into detail, there were sequential bile acids measurements and measurements for auto antibodies. And what the researchers have found, that you find changes in the secondary bile acids sooner than you find changes in autoimmunity. So this study adds further proof that the microbiome is playing a role in the risk for and pathogenesis of type 1 diabetes. Again, I will not go in an awful lot of detail here, but I did show in the beginning that co-medication might be something where metabolomics could play a role, and also finding out more about the pathophysiology of the typical downstream events of diabetes might be involved here. And those three mini examples show how that could go about. So in this case, there was a dietary intervention in a model of atherosclerosis. So obviously here the goal was to find out how different types of intervention that was targeted at introducing microbiome changes, how they actually affect the risk for atherosclerosis. There was another, this was another study taking a different approach in supplementing a nutrient in order to drive atherosclerosis risk down. and finding out on a molecular basis what the action of these interventions might be. And the third example, I don't know whether you see it fully or whether the sidebar is above it. This is for cross. I'm stumbling over the word to differentiate between cardiometabolic diseases. Finally, one topic that is near and dear to us and also to myself, because Monica mentioned that we are very active on social media, and my caption says scientific success stories with metabolomics and multiomics. And when I write it, I actually mean it. I think that you should never see any omics technology that you use in isolation. And obviously, there is a lot of knowledge also from other omic studies that you could use. And similar to how I have described it for the microbiome studies, where metabolomics could add functional insights to what you see on the microbiome composition side. Metabolomics has been used for about 15 years now in association with genetic studies to improve the power and functional insights of those genetic studies. I think the most striking example that I can remember is where a genetic association has been found in 500 individuals when it first had only been found in a cohort with 40,000 people. And the way that this is possible is because those researchers don't use just the genetics and the clinical phenotype, but they actually use the metabolic phenotype as an intermediary, and they look what is the association between the genes and the metabolites, and what is the association between metabolites and the clinical phenotype, rather than trying to make this this direct inference from the two layers. All right, that brings me to the end of the content pages. I would leave it up to Monica whether I show very briefly about our technology or whether we wrap it up.
No, I think that that's important because you kind of brought us up to this point, and then it would be great to, you're getting some clapping. It would be great to actually see how you, what you offer and how you wed the metabolomics to the omics.
Yeah.
Yeah, so go for it.
Okay. So there's a little bragging right there. Our technology has been used for more than 1,600 publications. I think we actually stopped counting quite a while ago. I think if you enter Biocrates in Google Scholar, you'll get more than 3,000 hits. But what this slide is intending to show is that you can publish very well based on metabolomics findings, and it's also very versatile in its use. You see the indication areas here on the right. And this is supposed to be gold, silver, and bronze medals because we didn't really know of any other of any better way to indicate the scientific impact that metabolomic studies have created in the past. So our technology, in a nutshell, is metabolomics kits that you could use in your own or in any partner mass spectrometry labs, as well as services. And what is the unifying thing about our technology is quantification. So you get molar concentrations of the metabolites that you measure rather than just peak areas or relative quantities. And it's always targeted. So by definition, you don't find any new metabolites with our technology, but you measure those metabolites that you target in a high quality and highly reproducible way. That's the main goal that we want to drive. And then you have more than 15 options to choose from. And on the one extreme, you could go for a very specific groups of metabolites, like the tryptophan metabolites or short-chain fatty acids. And the main reason why we have those very pathway-specific assays is that metabolites are very, very diverse in their concentrations, in how they behave in the mass spectrometer, whether they are even stable in many matrices, and it's just not possible to measure every metabolite as part of a broad range metabolomics study. On the other end of the extreme, you have the MX Peak 1500 XL kit, which actually measures more than 1,000 metabolites and more than 470 sums and ratios of those metabolites. So those large panel kits try to provide a little bit the best of both worlds between targeted and untargeted metabolomics. So the broad coverage of an untargeted metabolomics assay with the quantification and reproducibility of a targeted assay. But then you have, again, it's a broad assay that still does not cover the whole metabolome. And in some cases, you might want to drill more deeply. So for example, there are some bile acids in this broad assay, and there are some tryptophan metabolites in this assay, but because they are not as easy to measure, and especially downstream of quinuranin is very, very tricky to measure, you can't do that as part of such a broad assay. So that's why we also have more dedicated assays if you know that a very specific metabolic pathway is of interest. In the future, we obviously hope that metabolomics will make a clinical impact, and that the technology will serve a diagnostic purpose in the future. We are already certified as a diagnostic company, but all the solutions that you have here on the right at this point in time are research use only applications. I did mention that it always starts with pathophysiology, and I stand by that. Even if you might decide to go with the broad metabolomics approach, you should make up your mind about what might be relevant metabolic pathways. And I understand that especially clinicians often have a hard time defining that, but then that's where we come in, actually. So as an offering, we have a technology, but in terms of planning your metabolomics projects, we are always happy and here to help if you have any trouble deciding what is the best way for you to move forward.
So you guys can act in an advisory role as well.
Yeah, I mean, it's part of the job. I would say, I don't know how it is in the US, but at least in Europe, most funding bodies don't like pure fishing experiments. So you have to show at a certain level, if you go into a funding proposal, that you have made a deliberate choice in the metabolomics approach
right.
that you choose, right? So saying I have used,
could you advise,
I am planning
prior to could you then advise during the sort of the grant writing process?
Yeah, we can't write the whole grants. That's not possible from a capacity perspective. But I'm always happy if someone sends me a grant and asks me to review it. I will have an eye on it, and on the one hand, provide relevant information that hopefully makes the grant better. Because I see it quite often, to be frank, that someone describes pathophysiology on 40 pages, and then they go to the methodology section and say, I do metabolomics. And that's not good enough. At least in Europe, that's not anything that that reviewers really like, right? And often it's fairly simple to make these associations, right? So either the researcher has an idea anyway. If someone writes a grant for tryptophan assay, they obviously have an idea what role tryptophan assay plays. So it's more when someone is going for the broad metabolomics assay. So if they describe that the microbiome is playing a role, there's a couple dozen metabolites in this broad assay that are produced by the microbiome. If they write about inflammation and immune regulation playing a huge role. There's dozens of metabolites that are involved in immune regulation, right? So we're trying to match what they have described in the pathophysiology part with what's actually provided by the technology that they are going to use if they're funded, right? And I have already switched to the slide for the metabo indicator, which is the sums and ratios that I have described before. It's one of the key advantages of taking a targeted and quantitative approach. You can calculate with every number, but if you have actual concentrations, if you make a ratio between quinarenine and its upstream metabolite tryptophan, it's much more meaningful than if you do it based on relative data. And that would be one of the examples, right? If someone describes how important immune regulation is, and then they don't mention tryptophan metabolism, we would certainly advise them to write a few words about tryptophan metabolism being relevant and being involved there, and this ratio for IDO activity being something that you would cover with the approach that they are choosing. All right, that does lead me to the end of my presentation. So I hope I could show in a little bit more than 30 minutes actually that metabolomics could be important and relevant in studying the pathophysiology of type 1 diabetes and the development of diabetes related events, that pathways such or that factors such as host microbiome interaction and immunometabolism are playing a big role there, that metabolomics could nicely integrate with other technologies that you might already be doing. And yeah, if you come to the conclusion that Biocrates technology might be a good way to study metabolism type 1 diabetes, you could start with a good dozen metabolites in a very targeted way, or with more than 1,400 biomarker candidates in the largest solution that we have to offer. And again, if you're interested but don't quite know where to start, reach out to me and we'll be more than happy to help.
Thank you, Stefan. This has really been interesting. And I think the whole idea, that you're really saying, don't use omics in isolation without metabolomics is a really interesting and important consideration. And thanks for sharing, sort of walking us through your, use cases and, extending that into type 1 diabetes. I'd like to open it up to questions. If anyone has a question, please raise your hand or unmute yourself, drop something in the chat. I guess I would also say, how easy is, it to work, I see some people from the West Coast of the US here. How easy is it to work with you guys? You're based in Austria, is that correct?
That's correct. So there's two components to the answer. So first, yes, we have services, and if you want to use our service, so to do the analytical part of your study in our services lab, then the samples would have to go to Innsbruck. There's no way around that, and there's certain assays where there's no alternative either. If you want to measure oxysterols, the samples have to go to Innsbruck. The good thing is we have plenty of experience. So we have many projects from the US every year where samples come in. So logistically, this can be solved.
That pipeline is established.
Yeah, that works out nicely. Obviously, those samples are valuable, so it's always advisable to not just use enough dry ice to get the samples over here safely, but to actually use a dedicated logistics provider who would fill up dry ice if need be. And the other thing is, if you if you look back. So a lot of what we offer is actually kit-based. So in this case, there's not only the service that you can acquire from us in Innsbruck, but there is actually a physical product that we can ship to the US rather than you having to ship the samples to Austria. If you don't have mass spectrometry yourself, it doesn't matter. We'll be more than happy to put you in contact with one of our partner labs, of which there are maybe a couple dozen even in the US. Or if your institution does have mass spectrometry, but the kits are not established there, we could discuss about whether it's possible to establish the kits right where you work.
And these price points for these kits, or actually the services, are, all found where? In discussion with representatives, or they?
Yeah, that's one part. If you are from the US, you can actually go to our webpage. We do have a web shop, so the prices for the kits for US-based researchers are actually on the webpage. But again, if you want to know for your specific project, for your specific use case, for the specific essay that you might be interested in, you can always also just reach out to us, and we'll be happy to provide the information.
Fantastic. So any last minute questions from the group? Is everyone fully up to speed on what Biocrates does, what's their mission, and how to gain access to their kits and resources?
My understanding is that Biocrates has done some work on UK Biobank samples. Do you know how many metabolites were measured there?
Great question.
We haven't actually done UK Biobank. We have run a number of epidemiological cohorts, and in most of the cases, it was either the P180 kit for 188 metabolites or the Quant 500 kit with 630 metabolites. The Quant 500 XL is the newest addition to the portfolio, only available since January. So projects with this very broad solution are only picking up now.
See, maybe one more question specific to type 1 diabetes. Of course, like the disease relevant tissue, the pancreas is hard to access in the context of type 1 diabetes. Mm-hmm. People usually aren't going around biopsying the pancreas. Right. So presumably most of the metabolomics that has been done or will be done will be serum. How do you guys go about thinking about functional insights for something that's found in the serum in a disease context?
It's always an interesting discussion to be had. I very much like, again, to not see a single experiment in isolation, right? So if you just measure something in serum or plasma, you will get an association that might be very, very strong, but you can't prove based on this experiment that the signature that you get is from that organ, right? Especially as those are complex diseases. In all likelihood, the signature is not going to be just from that target organ. So I always like when researchers make this next step in trying to find out where their biomarker signature comes from. And this can be done, for example, by moving from the clinical study into a mouse model and take tissue samples from there. Or it's probably not a feasible approach for type 1 diabetes, but in neurodegenerative diseases, it's a frequent approach to not just use a serum or plasma sample from a patient, but to also use postmortem brain to find out what part of the signature actually comes from the target organ.
Okay, thank you.
Welcome.
Great questions. Okay, that was great. Really, really interesting, Stefan. I really appreciate your time, and hoping or know that this will be viewed many times when it's posted on our website. People typically listen and watch at their own leisure, and then hopefully you'll be getting some feedback from the T1D community and keep in contact regarding that. We greatly appreciate your walking us through this, these kits. And I guess I'll leave it at that and say, I guess you're in Austria, so we'll say Danke sehr.
Thank you very much. Well, it's been a pleasure.
Thank you. Have a great rest of your day.